All right, welcome back to the Kitchen Group Research channel. Today I want to tell you about some new work we've been doing in thinking about generative machine learning and approaches that we can use to solve inverse problems. So let me start by talking a little bit about the data set, the instrument that this is based on. We have built this little instrument here called Claude, and you can set an RGB LED, different levels for R, G, and B, and then you get an output at 3 or actually 10 different wavelengths. But today we'll focus only on 3 wavelengths that are roughly red, green, and blue. And the question here is, how do I set the LED to get particular values at red, green, and blue light? So we use a particular value here of 2 to the 14. That's just a count. The instrument has a 16-bit resolution, so it goes up to 2 to the 16. And so here we're going to ask, how do we set the LEDs to get 2 to the 14 in each one of these channels? Now the model here, this instrument's pretty linear, so down in the right-hand corner here you can see as I set the R level, you go in this linear fashion for red, green, and blue. So it's not a very difficult problem to solve this for, but that's a feature, and what I'm going to show you is that we won't have any trouble understanding why it works because it should. Okay, so we'll go ahead and talk about Claude now. It's a model system. It's a real system that makes real measurements with real noise, but it's a proxy for other kinds of systems like color mixing, or if you had a formulation with some input variables and then outputs that include things like viscosity or density, or if you were doing a media optimization, you might have variables like what yeast strain goes in, what are the ingredients of the media components, and then the outputs might be growth rates or protein expression. If you had catalyst composition and particle size, that might map onto reaction rate and selectivity, etc. So the model is going to be simple and the instrument is simple, but it's going to be related in a way. Now these real systems will have nonlinearities and other complications that I don't have in this data set, but the ideas are fairly general, and future work will maybe focus on some of these more difficult systems. So the goal today is really to introduce this new idea in conditional generative modeling of these systems and compare it to the other ways I know how to solve this. And if it works on this simple system, then it's likely it might work on a harder system. And we've done some harder systems, but I won't show them today. Okay, so a very conventional approach in solving inverse problems is to build a forward model. That is, I have some function of the inputs that predicts the outputs. And that function can be a linear model, a nonlinear model, a machine learned model, etc. And here I show a way we just use a linear model. We do a least squares fit of the inputs x to the outputs y and get the parameters. And then we use this nonlinear program down here to set a goal of 2 to the 14 for each of the outputs. And we calculate, given some parameters that go in, we then modify them iteratively until we get a reduction in error. And this is what the code looks like. You just put in minimize, you give it a guess, and you get a solution. And I use a Nelder-Mead method here. It's a simplex method that converges in this case pretty well. So this is a very conventional way of thinking about I build a forward model that is f of x equals y, and then solve for the x that gives me a specific y. All right, that one is very conventional forward model approach. There's a less conventional idea of using a backward model. So when you have a one-to-one mapping, you can just, instead of building f of x equals y, we could say f of y is equal to x. So we just invert the variables and train a new model. And this is also a linear model. Here I use partial least squares regression. That takes your inputs and does a PCA to eliminate covariance or collinearity in the inputs, and then solves it as another kind of linear model in that new feature space. We use 3 components because we have R, G, and B, and we can fit this model, and then we can make a prediction for a test some test point. And so the difference between this and the forward model is once we train this forward model, we simply evaluate at the outputs we want and get the inputs. So that works really well. And the model, again, this can be linear, nonlinear. I use the partial least squares here. We could also have just done linear least squares alone, but I thought it was fun to try the partial least squares. But you could also machine learn this. You could have a decision tree, a neural network, a Gaussian process, etc. So this backward model is really nice as long as you don't need to make a forward prediction, because now with this backward model, you would have to use a nonlinear program to say, what is the output I predict for, say, 1/2, 1/2, 1/2 at the inputs. Okay, now we're going to switch, because those are the conventional ways that I know about, and now we'll talk about a generative process and how we might generate samples to solve this problem. So while I work my way towards that, first I'll orient you to things you might be familiar with in generative processes. We have random number generators in NumPy. You can generate a uniform distribution, a Gaussian distribution. There are several other generators for other kinds of distributions where you can generate numbers that have a property of belonging to that distribution. So that's the first important idea, is that we already are familiar with some ideas of generation from the past. The newest ways that people think about this is image generation. So things like DALL-E can generate an image for you from a description of words, and ChatGPT is also a quite famous generator. It generates text from a word distribution. And the critical idea I'm going to introduce here is that we're going to generate conditional samples. That means we specify some properties. So when you generate an image with DALL-E, you don't get a random image. You say, I want an image of a landscape. And that conditions the image to be of that sort. And it does that by setting some properties of the sample and then generating the rest of them. So I'll show you how that works in a little bit. All right, there's another way to generate. Instead of simply generating samples, we can transform one distribution into another distribution. And so I showed this idea here. On the top you see what's basically a uniform distribution, and on the side here you have a Gaussian distribution. So if I generate a random uniform number on the x-axis, let's say 0.6, then you come up here and you come over to here, and that corresponds to this Gaussian distribution of a little bit greater than 1. So here if I generate lots of uniform numbers along this axis, and I transform them by the cumulative distribution function of Gaussian, that's this line here, then I can transform one distribution into another. So this particular one has an analytical function where we can just calculate. If I put in the uniform number here, I'll get a Gaussian number over here, and that allows us to think about generating a sample and then transforming it. So if we knew what a distribution for the solution space was, we would be able to find this transformation function, and then by sampling uniform random numbers, we would generate samples in the solution space. That's sort of where this is heading. All right, so how does conditional sampling work then? The idea of conditional sampling, here we have a two-dimensional Gaussian distribution of dots, and if you look at the distribution in Y, you see we have this broad distribution here. And if you look at the distribution in X, you see this broad distribution here. Now, we can't just pick any points in this space. They're not very likely. The most likely ones are where it's dense here. So now, if I condition and say I want to find X values where Y is equal to 1, so I'm specifying Y equals 1, you come across here, you see out here where it's white, there's like no chance you have a value out there, no real chance. But all of the X values are in this range here. And so over here I have this idea that if I specify Y equals 1, the orange spots are the most likely values of X. In other words, I can update the probability for X once I specify what the value of Y is. And now if I sample from the orange Gaussian, then we can find likely values of X where Y equals 1. This is the generative approach with conditional sampling. And you can expand it to higher dimensions where if I know the distribution, the full joint probability distribution of a bunch of variables, and then I specify one or more of them, then I can update the full probability distribution and call that the conditional probability, and we sample from that. And as long as we have things like Gaussians, those are easy to sample from. All right, so how do we use this idea for inverse problems then? What we have to do is either learn the distribution of input-output pairs, or we need to learn the transformation function between the input distribution and output distribution. And that's where machine learning is going to come in. And once we know those, then we can draw samples from that distribution and use it to solve our inverse problems. So I can specify I want an output with these properties and generate the inputs, or I could specify I want the inputs and generate the outputs. So we're going to use two different approaches here. The first approach is to learn the distribution, the joint probability distribution, and we use the Gaussian mixture model for that. This is a very straightforward model that if you look at this data here, you represent the joint distribution by a sum of Gaussians, and it's kind of like a piecewise linear model, but it's really a piecewise Gaussian. So here we have one Gaussian for this red chunk, one Gaussian for the green chunk, one Gaussian for the blue chunk, and where you don't see any color at all, the probability of those points existing is extremely low, and so you can see that when you're in this region, the red one will dominate, in this region, the green one will dominate, in this region, the blue one will dominate, and we can build what we call these GMMs for learning this distribution. And now we can go and, just like I showed you before, if I want a specific value here, say 0.5, then we condition on y equals 0.5, update the probabilities, and then we will be able to sample in this red region and this green region by using the code. And so it's very easy to make. This is the code for making a GMM. It's a two-step process. There's sklearn mixture has a Gaussian mixture model, and then that's what we do the training with, and then we generate this Gaussian mixture regression model from the GMR package. And once we have the GMM, it's possible to sample it. The other idea is to learn the transformation of one distribution to another. And this is what's called conditional flow matching or flow matching generative models. Normalized flow is another word. And so there's a couple of ideas that are illustrated here on the left here. At the front, you start out with one distribution, and as you move into the screen, it slowly is getting transformed into a new distribution that's shown in the back. Over here is a different way of thinking about it. You have this, say, normal distribution here, and as you go forward in time from 0 to 1, the Gaussian distribution here is slowly transformed into these two peaks as an output distribution. And the way that works is shown here. We have this vector field, and you have a differential equation that allows any point here to flow through the vector field and get mapped onto a new point over here. So that's sort of the idea. It's complicated math that makes it actually happen. Luckily for us, the code is very straightforward. Here I use a forest diffusion model, and this combines the random forest for training with the diffusion model, and we have just the forest diffusion model here. And then again, with the forest model, we can conditionally sample and say I want an output in this region, and then find here by kind of going back here what is the corresponding input, and that's all there is to it. Okay, so I did run these for all 4 of those models, and I just showed the results here. The results aren't particularly important other than they're almost all the same. So we can do the forward linear model with NLP, and we get these inputs for RGB to get those outputs. We can do the backward partial least squares, the GMM, and the forest diffusion, and we get roughly the same answer for all of them. And so that mostly is just a demonstration that we can use these generative ideas, either learning the probability distribution or that transformation function, to invert this problem for that. So that's the end. There is a preprint on ChemArchive. You can read all about the details, see all of the code, all of the all of the figures and everything are in there, and hopefully you'll find this an interesting idea. And we have some subsequent work in using generative models more generally in optimization, also for more nonlinear functions in there. So I hope you enjoyed this and learned something new, and we'll see you next time.